Alright, in this video, we think about the number of elements in the set with infinite cardinality. That is, the set of natural numbers, the set of integers, the set of rational numbers and real numbers. These sets all contain infinitely many elements. So which sets are bigger than others? You might think that there are more integers than natural numbers, and there are more rational numbers than natural numbers or integers, but that's not actually true. And it's really difficult to compare infinity against infinity, but we can show that these three sets contain, in a sense, the same number of elements. On the other hand, the real number is really different from all other sets. So the set of real numbers contain far more elements than these sets. And we say these sets are countable. On the other hand, the set of real numbers is uncountable. So we'll make these notions clear later. Okay, let's start. So first consider a very simple set. Let's say 1, 2, 3, 4. So this contains 4 elements and integers 1, 2, 3, 4. And consider another element, another set made of A, B, C, D. Okay, so both of these sets have 4 elements, and we can define bijections between them. For example, 1 goes to A, 2 goes to B, 3 goes to C, and 4 goes to D. So this defines a map or a function from this set to this set. Okay, so if there are same number of elements in two sets, we can always define a bijection. By the way, this is not the only bijection we can define, and there are many other bijections possible. For example, 2 can map to A and 1 can map to B, and there are many other possibilities. So in this way, the existence of bijection implies the same number of elements in two sets, the set of domain and the set of codomain. And this observation can be generalized to any finite set. For example, if we have a set consisting of n elements, x1, x2, and so on, then we can enumerate all elements in this way. And note that we have this index here, 1, 2, 3, and so on, up to n. So there are n numbers appearing in this expression. So it is trivial to define a bijection from the set of n natural numbers, 1, 2, 3, and so on, up to n, to this finite set. So this is trivial bijection. So this 1 corresponds to x1, and 2 corresponds to x2, and so on. So now, what if there are infinitely many elements in a set? Is it possible to define a bijection from the set of natural numbers to the set of consisting of infinitely many elements? Is it possible? The answer is sometimes yes and sometimes no. When it is possible, then we can write that set like x1, x2, x3, and so on in this way. So we can label each element by a natural number. But sometimes there are so many elements that we cannot enumerate like this. It may be hard to imagine how it is possible, but when infinity is involved, something strange can happen. So be careful. Now, based on this intuition, let's define the notions of countable and uncountable sets. Okay, so here's the definition. A set X is a set. So let X be a set, and we say X is countable if the elements of X can be enumerated. Rated as x1, x2, and so on. So when the cardinality of X is finite, then that means X can be the elements of X can be enumerated as just n elements. So that is n finite. And when the cardinality of X is infinite, but countable, then that means the elements of X can be enumerated as x1, x2, x3, and so on. So in other words, in this case, there is a bijection from the set of natural numbers to this set X. And in this case, when the finite case, there is a bijection from a finite set of natural numbers to this set X. So together, we can say that if there is a bijection from some subset of a natural number to that set, then we say that set is countable. Okay? So if X is not countable, we say X is uncountable. Easy, right? Uncountable. So we'll see an example of an uncountable set later. By the way, some mathematicians or textbooks use a different convention. So sometimes we might distinguish finite and infinite and countable sets. Okay? Finite set is just a finite set, and a countable set is a set where there is a bijection from the set of natural numbers to that set. Okay, so in that case, a countable set is necessarily infinite set. Okay, so in that case, if we want to mention both of these cases, finite and countable, we say at most countable. Or we say discrete. Okay. So this is either finite or countable. And together, so we use these terms. Okay. If a set is not at most countable or discrete, we say that set is uncountable in that case. Let's see a few examples. Consider this set, negative natural numbers. Okay, so what does that mean? So it's just a negation of each natural number. So n is a natural number. So that is something like -1, -2, -3, and so on. So is this a countable set or uncountable set? Of course it is countable because there is a obvious bijection. So from natural numbers to negative natural numbers given by n maps to -n, right? So this is 1 to 1 and onto, therefore it's a bijection, obviously. So therefore this set is a countable set. And next example, how about the set of integers? Is this countable or uncountable? So to show that this is countable, we need to establish a map from the set of natural numbers to the set of integers, which is bijective. So how is that possible? Intuitively, it seems that there are more elements in the set of integers than the set of natural numbers, but both are infinities, so something strange can happen. So how can we establish the map? Okay, let's say f of n is defined in this way. Okay, negative n minus 1 over 2 if n is odd, and negative n over 2 if n is even. Then this is actually a bijection from natural numbers to integers. You should prove that, okay? But let's consider some examples here. So when n is equal to 1, then 1 is odd, so n minus 1 is 0. So that is 0. F of 1 is 0. When n is 2, then f of 2 is even, so negative 2 divided by 2 is negative 1. When n is 3, then we have f of 3, it's odd, so 3 minus 1 is 2, and 2 divided by 2 is 1. Okay, can you see the pattern? So this is even, so divide by 2 and multiply by negative 1. That's negative 2. And n is 5, then f of 5 is, it should be positive 2. And you should try that. So actually for any integer, we can find a natural number that maps to that integer. And for each natural number, we have a different integer coming out of this function. So it is a bijection. And you should prove that more rigorously. Okay, so anyway, so in this way, we can prove that the set of integers is countable. So in a sense, that there exists a bijection between these two sets, we can say that there are the same number of elements in these sets. So there are as many integers as natural numbers. And here's a trivial theorem that says any subset of a countable set is countable. Okay, I think this is trivial, so you should think about it, how to prove this. And example is this. 2 times z. So this means the set of even integers, okay? How can I write this? Okay, 2i, where I is integer. Okay. So this is obviously a subset of integers, and we have just seen that the set of integers is countable. So the set of even integers is also countable. And same for the set of odd integers. Next, let's consider a little non-trivial example. Consider a set indexed by actually 2 indexes, 2 natural numbers. So something like xpq, where p and q are natural numbers. So what this means is that we can enumerate the elements of X in a two-dimensional array. That is X11, X12, X13, and so on. And X21, X22, X23, and so on. And X31, X32, X33, and so on. Okay. So each row and each column continues forever. Okay. So is this set countable or uncountable? So the answer is it's actually countable. So we can arrange this two-dimensional array in a sequence. For example, first take this, and then take this, and this, and then take this, and this, and so on. Okay, so the sum of indexes becomes constant. So 1 plus 1 is 2, and first one x1 1, and next x1 2, and x2 1. So the sum is 3. 1 plus 2, 2 plus 1, and then x1 3, x2 2, and x3 1. So that's this, and next one, x4 1, and x3 2, x2 3, x1 4. So there are 4 elements on this row, I think, and so on. So we can actually make a bijection from the set of natural numbers to this set. Okay, so 1 and 2 and 3 and so on. Actually, you can make a formula mapping each natural number to two indexes like this. So, you should try to find it. So anyway, so we can see that this set indexed by two natural numbers is actually countable. Now, based on this example, we prove the following theorem. That is the union of countable sets. Actually, finitely many, countably many. Countably many countable sets is countable. Okay, so you know what a countable set is. What does countably many means? So that means either finite or infinite, but infinite in this case means countably infinite. Okay, so at most countable number of countable sets. If we have such sets, then we take a union of it, then the resulting set is also countable. So let's prove that. So suppose we have countably many sets of which are all countable. So that means we have sets x1, x2, x3, and so on. And for each set, we can write their elements like this. So the elements of x1 is x1 1, x1 2, x1 3, and so on, because it's countable. So we can enumerate all elements in this way. And for the second set, x2, we can enumerate all its elements as x21, x22, x23, and so on. And same for x3, x31, x32, x33, and so on. So if we take the union of all these sets, so x1 cup, x2 cup, x3 cup, and so on, then we can arrange the elements of this union in two-dimensional array, just like we did for the previous example like this. Okay, so the elements are this. x31, x32, and so on, right? In practice, some of these elements may be the same, so there can be actually less elements than this one if some of them are finite sets. But anyway, the number of elements cannot be greater than the sum of these elements, right? So since this is just a two-dimensional array of elements, as we have seen in the previous example, this is countable. So we are done. Okay, using this theorem, we can again prove that the set of integers is countable. So here's an alternative proof. So integers can be, the set of integers can be decomposed into unions, a union of natural numbers and negative natural numbers, and the set consisting of only one element, 0. And by definition, the set of natural numbers is countable. And it's trivial to see that the set of negative natural numbers is also countable. And this is finite, so it's countable. And according to the theorem, the union of countable sets is countable. Therefore, the set of integers is countable. We are done. Okay, next we prove a similar but very different theorem that says the Cartesian product of a finite number of or finitely many countable sets is countable. So this looks like very similar to the previous theorem, but the significant difference is here. A finite number of countable. It's not countably many. Okay. In the previous theorem, we can make the union of infinitely many countable sets, as long as this infinitely many is countable, right? But here we limit to a finite number of sets, countable sets. Okay. This is a big difference, and we should pay attention to it. By the way, remember what a Cartesian product is. Cartesian product between two sets is something like this: A times B, which is a set consisting of pairs, where each element of the pair comes from the respective sets. Okay, so this is the Cartesian product between A and B. Let's see a more concrete example. Suppose A is a set of 1 and 2, and B is a set of A and B. Okay, so what is the Cartesian product between these two sets? Okay, so we take all combinations of elements between A and B. So this is 1 and A, for example, and 1 and B, and 2 and A, and 2 and B. So this is the Cartesian product between these two sets. Okay, and now we extend this to countable sets. Okay, so the number of elements of A and B may be infinite, but countable. Okay, so let's prove this theorem. And first consider the Cartesian product between two countable sets. So let's say A is a countable set. Let's see n, where n is a natural number. And B is also a countable set. Okay. So the Cartesian product between these two sets is made of pairs. Let's say AP and BQ, where P and Q are natural numbers. Okay. So this is countable because if we write each of these pairs as XPQ, AP and BQ, so this P is this P and this Q is this Q, right? So we can write each element of this Cartesian product as this. But so this is like XPQ, where PQ are natural numbers, okay? But we have seen that this set is countable. So this Cartesian product is countable. Okay, more generally, we use mathematical induction. Okay, so let x1, x2, and xn be countable sets. And suppose, so this is induction hypothesis, okay? Suppose x1 times x2 times and so on times xn is countable. Now, let xn plus 1 be a countable set. Okay. Now, we want to show that x1 times x2 times and so on times xn plus 1 is countable. Okay, but this is same as this. x1 times x2 times and so on times xn plus 1. But this is countable by the induction hypothesis, right? And this is countable. So this is actually the Cartesian product between two countable sets. Therefore, this is countable. Okay, and we are done. So assuming this is countable, we have shown that this is countable. So by induction, the Cartesian product of finitely many countable sets is also countable. And we are done. Now, using this theorem as a corollary to this theorem, we can prove that the set of rational number is also countable. Okay, so how is it possible? You know, the set of rational number seems to contain a lot more elements than the set of natural numbers, but still, it is countable. We first consider the set of strictly positive rational numbers. for simplicity. Rational numbers. Okay. So that means this is the set consisting of something like this. So since it's strictly positive, then m and n are natural numbers, right? But this m divided by n can be written as m as a pair of n and m, right? So there is a bijection between this expression to this expression. So the set of strictly positive rational numbers is actually the same as the set of pairs of natural numbers. And we have just proved that this set, such a set is countable. Okay? And similarly, we can show that the set of strictly negative rational number is also countable. And in addition to that, we have 0. So the union of these countable sets is also countable according to a previously proven theorem. Therefore, after all, the set of rational numbers is countable. So far, we have only seen countable sets, and you may be wondering if there are any uncountable sets. And here is one example, which we prove as a lemma. Okay, so let 2 to the power of n be the set of all maps from natural numbers to the set of 0 and 1. Okay, let's name this set as 2, okay, because there are 2 elements. Then this set is uncountable. So how do we prove this? What we want to prove is this is uncountable, and uncountable means not countable. And as we have seen before somewhere in some other videos, if we want to prove something is not something or negative statement, then it is often, not always, but often useful to prove by contradiction. So here it goes. So suppose 2 to the power of n is countable. Then what does that mean? It means the elements of this set may be enumerated by indexed by natural numbers. So then we can write the elements of this set as like f1, f2, f3, and so on. Okay, this may be finite, not finite, maybe not finite, but actually it's infinite because the domain is natural number. So there are infinitely many combinations of assigning 0 or 1 to each natural number. So anyway, so suppose if this is countable, then we can write elements of this set as this. Okay, so this also means for any map from natural number to this 2-element set, then there exists some natural number such that fr is equal to this function. Okay, so for any function from natural number to 0 or 1, then that function must be one of these elements. Okay, that's what countable implies. Okay, now let's define the following map. For any natural number, we define g of n as follows. Okay, this is equal to 0 if fn of n is equal to 1, or 1 otherwise, that is if fn of n is equal to 0. Okay, so since we're assuming this is countable, we can just enumerate all values. F1 of 1 had some value, and F1 of 2 had some value, either 0 or 1, F1 of 3, and so on. And similarly, F2 of 1, F2 of 2, F2 of 3, and so on. And F3 of 1, F3 of 2, F3 of 3, and so on. So, which FR should correspond to this G? Okay. Well, exactly identifying the function is not so easy, but it is guaranteed that there is some index, natural number R, such that fr is equal to this G, this function G. Okay, so let R be a natural number such that fr is equal to G. Then, what is the value of G of R? Okay, so this is, of course, either 0 or 1. So this is either 0 or 1. So which one is it? Now, since G of R is equal to fr of R, okay, then if G of R is equal to 0, according to the definition of G, okay, that means GR is 0 if fr of R is equal to 1. Then fr of R is equal to 1. Okay. And if G of R is 1, similarly, then fr of R should be equal to 0. But G of R must be equal to fr of R. So this is equal, but this is not equal. And this is not equal. Either way, it cannot be equal. So this is a contradiction. Therefore, our assumption was wrong. That is, this assumption was wrong. Therefore, this set is uncountable. And we are done. By the way, this proof, the key to this proof is how we define this function g, right? And this g is actually defined in terms of the diagonals, okay? So we took this for n equal to 1, and this for n equal to 2, and this for n equal to 3, and so on. So we are using these diagonal elements to define this new function g. Then we derived a contradiction. This type of argument is called Cantor's diagonal argument. Maybe you should look up Wikipedia or something. Diagonal argument. And this type of argument appears in many places in mathematics, and it's pretty useful. So it's good to remember what this is. Now, using this lemma, we can prove that the set of real numbers is uncountable. Okay, so let's prove that. Actually, we don't have to consider all of real numbers, but it suffices to show that this interval, the real numbers between 0 and 1, including both 0 and 1, is uncountable. So this is just a subset of all of real numbers. So if this is uncountable, then it's obvious that the entire real number is uncountable. Okay, so how do we do that? Okay, to do that, we express the real numbers in this interval in the binary form. Okay, so that means every real numbers can be expressed in terms of 0 and 1. So since this is less than or equal to 1, so for every real number in this interval, we can express are in terms of binary format. So it's a sequence of 0 and 1. Let's say A1, A2, A3, and so on. So each of A1, A2, A3, and so on, they are either 0 or 1. So that means for each real number, there is a map. So for each real number in 0 and 1, there is a map from natural number to 0 and 1, right? So these are natural numbers. So the first digit, second digit, third digit. For each digit, there corresponds either 0 or 1. So that determines a map from natural numbers to 0 or 1. Okay. So this is actually bijection. So if we determine any binary number here, then there exists some real number in this interval. So that means this real number to this function f is a bijection. Okay, so that means the set of real numbers, this set, and this set that was used in the previous lemma are actually the same set, or they have the same number of elements because there's a bijection between them, right? So this interval between 0 and 1 and this map, the set of maps. So there is one-to-one and onto correspondence between them. Therefore, if this is uncountable, this must be uncountable. And we are done. So, in summary, we have seen that the set of natural numbers, the set of integers, the set of rational numbers, they are all countable. And the cardinality of these sets, it's represented by some special symbol called aleph. I don't know how to write this one, but it's something like this: aleph 0 or aleph naught. Aleph is a Hebrew, the first letter in the Hebrew alphabet. Aleph 0 or aleph naught. So it corresponds to Arabic aleph. And so they are all infinity, but for convenience, we just call it aleph 0. Okay. On the other hand, the cardinality of the set of real numbers is uncountable. It's infinite, but uncountable. And uncountable. And its cardinality is called aleph 1. Okay, so this is 0 and 1. And we have seen that there is a bijection from, actually we have seen the bijection between this and this, but there is a bijection actually between real numbers to the set of all maps from natural numbers to 0 and 1. And the cardinality of this set is 2 to the, well, roughly speaking, I mean, intuitively speaking, it should be 2 to the power of the cardinality of the natural number, which is the cardinality aleph 0. So that should be equal to aleph 1. Okay. So we have different kinds of infinities. So this is infinite and this is infinite, but one is countable, but the other is uncountable. And the most important lesson here is that when infinity is involved, something strange can happen. So be very careful. Okay, that's all for this video. See you later.